Thank you. It's great to be here and get a chance to speak. So this is research that I've actually talked about here before a year ago. I think only one person in this room was here then, but I've got more results since. So this is commutative algebra research that is both inspired by and applicable to actual neuroscience, which is kind of neat. So where this comes out of, no, we're just going to do the fun way. All right. So the setup is you've got some sort of pen. You've got, for example, a rat running around the pen, and you've got, you can look, the rat's moving all around throughout, say, a 10-minute window. And you noticed every time the rat is over here, a particular set of neurons is firing. And in particular, there's some neuron that always fires when the rat is here and nowhere else. And then over here, there's a different neuron that fires only here and nowhere else. And because of that, those are called place cells. So in an actual recording of place cells, they would probably be recording about 100 neurons. But here's a diagram of 3. So maybe this is the place where neuron 1 is firing. Here is the place where neuron 2 is firing. And here is the place where neuron 3 is firing. And sometimes we call the ambient space the pen X. So this is a diagram of physical space, not of something happening inside the brain. But the thing that people often look at is which sets of neurons fire together. So if we look at every point in the space, we can record a binary string for the neurons that are firing at that point. So we've got points where none are firing, and that's going to correspond to the binary string 0, 0, 0. We've got a point where 1 is firing, so that'll correspond to 1, 0, 0. We've got just 2. We've got 1 and 2. And we've got 1 and 3, but 3 never fires alone. So if we look at this collection of what are called code words, this is the neural code. And it's going to be a subset of all binary strings of length 3, or if you have n neurons of length n. So this is inspired by place cells, but in fact, there's lots of aspects of the brain where recording a neural code is useful, particularly in the olfactory system. Or if you had anything with binary code words, you could study this as well. If anyone's done any coding theory, the thing that's different here is that these codes are usually not linear. They're pretty random, often sparse. And a thing to note is that any set of code words is realizable in some R to the D, but it might not be in 2 dimensions if you're not working with place cells. So the big questions that people would really like to answer using neural codes are really, how can we tell how these work? How do we know why there are place cells in particular places? And in particular, can we identify an animal from taking multiple recordings of that animal in different spaces? Are there things that particular animals always have in common? And second, can we identify features of a space? So if we record a whole bunch of rats in the same pen with the same setup, say with a food bowl in the same place, will they have common features? Is there something that place cells tend to record? And of course, we'd really love to know this for people, but you can't do this kind of research on people. So we're learning for things like rats and bats and impressively fish, and hoping to get information about humans from that. So if what we want to do is detect when arrangements of place cells are similar to or different from each other, what we're really looking for is how do we classify arrangements of place cells? How can we get invariants of arrangements that will tell us which ones are like each other? And that's where this commutative algebra research comes in. So I'm going to jump through several papers in one go. So these are a mix of results of Curto, Itzkov, Velas, Cuba, and Youngs, and Gunturkin, Jeffries, and Sun. This first paper introduced neural ideals. This paper polarized them. I'm just combining it. So the polarized neural ideal is going to be an ideal of the following ring. So we've got two variables for each neuron, an x and a y. And our coefficients are just 0 or 1 because we really only care about binary. And it's consisting of one generator per relation of the type some intersection of u sub I is contained in some union of uj. And this is going to correspond to the generator, which is a product for each of the ui's on the left. We're going to get an xi. And for each uj on the right, we're going to get a yj. Critically, it's a square-free monomial ideal. Commutative algebraists love these. There's so much we can do with them. And we also want to say such that sigma intersect tau is empty and no ui or uj can be removed. And if you add those assumptions, then this is unique. So any arrangement, any neural code corresponds uniquely to one of these ideals. So for example, if we look at this one, we've got one of our relations is that U3 is contained in U1. Is this still visible or is it too low? Too low. Okay, I'll put it up. So U3 is contained in U1, and that's going to give us the generator X3Y1. And then also U3 and U2 just never intersect. That counts. The right-hand side is just empty. So U2 intersect U3 is empty. And that'll give us the generator X2, X3. And notice that in both of these relations, I can't remove anything from either side and have the relation still be true. So you might look at this and go, yeah, these are going to be like minimal generators in some sense. Sort of. So here's another example. Let's do. So here I've got U3 is contained in U2 is contained in U1. So here are some relations. And these will actually correspond to generators of the ideal. But these aren't the only minimal receptive field relations. We actually also have to include U3 is contained in U1. So the point of this example was to show you that you might go, like, these are enough to describe what's going on here. But in fact, since this relation is also true, we have to add it as well. So the relations are minimal with respect to removing UIs and UJs, but we have to have every relation that's true, not just like enough to describe it. Okay. So we've got these square-free monomial ideals. Since we've got them, we can take their minimal free resolutions, Betty numbers, etc., all of these nice algebraic invariants, and that's what we're going to do. But I want to work with a very particular family of codes. So these are called inductively pierced codes. And these were originally defined by Curry, Jeffs, Youngs, who's also in this paper, and Zhao. Oh, I forgot to write down the year. Sorry about that. So this is a family that you can think of as being in general position. It's a little more specific than that. The actual definition is annoyingly technical. So I'm going to do this by picture. And I'll build one inductively for you. So here's my ambient space X. The first thing I'm going to draw is a zero piercing, because it's intersecting nothing. I mean, the first one's always a zero piercing. Next, I'm going to draw a 1 piercing. It intersects the first firing field in such a way that every possible intersection of a subset exists. There's a place where both fire, where each of them fire separately, and where neither of them fire. I'm going to draw another 1 piercing. So again, we have every possible intersection. Next, I'm going to draw a 2 piercing. So it's a 2 piercing in that it intersects both 2 and 3, and we see every possible intersection of them. And then finally, I'm going to draw a 1 piercing that's a little bit different. So this U5 is a 1 piercing of neuron 2. So we see every possible intersection between 5 and 2, but they all take place inside of U1. So inside of U1, we have a place where both U2 and U5 fire, where each of them fire alone, and where neither of them is firing. So that's also allowed. So I want to give people a second to stare at that.
So when you make one of these, the union of all the UIs is always connected, or not necessarily?
Not necessarily. I've been drawing them connected because those are good examples, but this is totally fine.
You make as many 0 piercings to start as you want.
Yeah, and you can actually do 0 piercings later as well. So you could have drawn this structure and then another 0 piercing after. The order is often not unique. So a thing we can count from here is how many piercings of each type we have. So we'll call these numbers J's. So I could write J0 is 1. There's 1 0 piercing. J1 equals 3. And J2 is 1. If I wanted to really pay attention to the fact that the 5th firing field, it's not just a 1 piercing the same as the others, it's contained in something else. I can change this and start writing 2 indices, where the first one is what kind of piercing, and the second one is how many things you're contained in. So if I do that, I'll get J00 is 1, J10 is 2, J11 is 1, and J20 is 1. And notice, a priori, it's not clear that these numbers are well-defined for the code. We know it for the way we drew it, but for the code, a little ambiguous. So something that's really lovely about these, though, if you're inductively pierced, the polarized neural ideal has a really nice structure. So I'm going to write down this one. So for this, any 2 neurons can either have the relation that they don't intersect, or that one's contained in the other. Otherwise, they intersect and we don't write anything down for that pair. So here, all the generators are degree 2. If we assume that every neuron fires, we can force that always. And for any pair ij, we have at most 1 generator, and it's either 2 x's, an x or an x and a y. So algebraically, these are like pretty good as things go. So that is a theorem that generated in degree 2 stuff. So let me talk about the invariants we're computing and how we found out which ones we needed. So this is current work by the 4 authors listed up there. So we have a few examples that give us a sense of like what we're trying to distinguish. So J1, this we can draw as this. So all we know is 1 and 3 don't intersect and 2 and 4 don't intersect. So this is a realization of it. And this is not inductively pierced. Versus J2 is going to be x1, x4, x3, x4. And this one is inductively pierced. And let's put the other one here. And J3 is another one that's inductively pierced and is pretty close to J2. So it's x1, x4, x4, y3. So this one, it's almost the same. The difference is here, one of the one piercings is inside another firing field. That's literally the only difference between J2 and J3. So the invariants we wanted to compute are Betty numbers. If you know them, great. If you don't, some numbers. So for J1, the Betty numbers, if I draw a whole Betty table, I'm going to put it, if I put it here, will it be visible? Okay. So this is for J1. So I'm putting the homological degrees at the top, and the total Betty numbers are 1, 2, 1. And then this one will be for J2. And these have the same total Betty numbers. So if all we look at is standard Betty numbers, we can't distinguish inductively pierced from not inductively pierced. But if instead we go to the graded Betty numbers, then we can. So for this one, we get the following table. And for this one, we get a table like this. So graded Betty numbers look like they're enough to distinguish between inductively pierced and not inductively pierced. But the question is, can they distinguish between 2 and 3? Yeah.
Why is collateral not inductively? Is it a requirement that if I intersect two things, then
They have to intersect each other.
okay.
So we can draw, say, the top 3 just fine, and then when we go to draw the 4th, it breaks. Yeah. So this one has Betty table actually same as J2. So this tells us that if we want to distinguish whether the firing field is contained in another one or not, these J's with the double subscripts, then we actually need to go to a multigrading. So to deal with this problem, we picked a multigrading. So we're going to set the degree of xi to be 1, 0. And the degree of yi to be 0, 1. So we just want to know whether we've got an x or a y in the generator. Because here, something like xi, xj is telling us two things don't intersect, whereas an xi, yj is telling us one is contained in the other. So this will help us tell the difference. So we have two main theorems. So given neural code C and J, its polarized neural ideal, I'm going to abbreviate that PNI. If J is generated in degree 2, it has no generators that are yi, yj. So we don't want the union of any of these to be the whole ambient space. And no ui is equal to uj. If you have that, you can just remove one. So then C is inductively pierced if and only if the regularity of of S mod J is 1. And by the regularity, I mean, what's the lowest row of the Betty table with a non-zero entry? So you can see in these examples that J1, which was not inductively pierced, has one more row in the Betty table than J2 and J3. So you can see that pattern there. So already we have a way of detecting these inductively pierced codes. So now if we want to actually distinguish them, so suppose C is inductively pierced. J, its polarized neural ideal. Then we actually get a formula for those J sub KLs, so the ones with two subscripts. That's J sub KL is, formula's messy, not really the point. S here is the ambient ring. Formula is a little messy at the end. All I need you to get from this is we've got these multigraded Betty numbers. And if you know the multigraded Betty numbers, you can find the JKL. And what's nice about this is the Betty numbers depend only on the ideal and hence only on the neural code. The choice of piercing order won't affect the Betty numbers. So this actually tells us that the J sub KL are totally independent of our choice of piercing order. So this is also invertible. If you wanted to find the betas in terms of the J's, you could. But what's really nice about this is we're saying that these Betty numbers, this purely algebraic thing, is actually telling us a really important property of these inductively pierced neural codes. And better yet, you can just compute the algebraic thing in Macaulay 2. I've made a neural ideals package that'll be released soon. And then you get these things. And if you had a diagram of 3 place cells, like fine, you can tell what they are. But if you have 100 cells, maybe it's not so easy to come up with a piercing order or to tell how many piercings of each type there are. But the Betty numbers with a fast enough computer, you can definitely just compute them. Cool. And we also have some results on things like the projective dimension in the paper, which is now up on arXiv. So that's all. Thank you.